Okay, so let's continue with the numericals of chapter 2. So this is 2B, question number 22. So what does the question say? Natasha is being constantly scolded by her mother for being unfit. Okay. She decides to lose weight by lifting a mass of 10 kg by 0.5 meter 100 times. Assuming that potential energy lost each time during lowering of mass is dissipated, calculate the work done by her against the gravitational force. So it's easy only. What's given? The mass that Natasha is lifting, the mass is 10 kg. What else is given? Displacement is 0.5 meters 100 times. So, okay, let's leave that. Calculate the work done by her against the force of gravity. So, what will be the work done? How will we calculate the work done? We know that work done is mgh, right? Okay, let's take this as h. And since she's doing it 100 times, so it'll be 100 mgh. Then it'll be 100 into mass is 10, displacement is 0.5, so 5 by 10, and g is not mentioned. No. If g is not mentioned, we have to take it to be 9.8. Okay. Then let's cancel. So 10 and 10 we can cancel. Then 98, 980 into 5. 4900. That's easy. All right. Let's see question number B. This part is interesting. If fat stored in her body supplies 3.8 into 10 to the power 7 joules of energy per kg. What does that mean? See, Natasha, she's fat, right? That's the question. That's what the question says, okay? And why she's fat? Because in her body she has lots of fats. Yes. Now, according to the book, 1 kg of fats supplies 3.8 into 10 to the power 7 joules of energy. Okay. 1 kg can supply this much energy. The question is asking how much fat did she burn in producing this much of energy? Okay. Given that the efficiency is 20%. Okay. The efficiency is 20% means efficiency is 20%. Now, what is the formula of efficiency? Yes? Input and output. What input? What output? Yeah. You give me a hint. Okay. It's work input. Oh, sorry. It's output by input. Work output upon work input. Since it is in terms of percentage, so it will be 100%. So efficiency is given to be 20%. Work output. Work output means how much energy do we need, right? So how much energy do we need? 4,900 joules, and we have to calculate the work input. So basic math, this will go up. Okay, so that means the fats must give 24,500 joules in order to get the output 4,900 joules. Try to understand why is fat producing more energy. The fat itself has to produce more energy so that a less amount of energy can be received. Why? Because efficiency is 20%. Are you getting? So this much energy we have to get, but we have to find what mass of energy is required. So how do we find that? See, 24500 joules of energy is produced by, oh sorry, not 24500, that number, 3.8 into 10 to the power 7. 3.8 into 10 to the power 7 joules of energy is produced by 1 kg of fat. So that means, elementary method, 1 joule of energy is produced by 1 divided by 3.8 into 10 to the power 7 kg of fats. And finally, therefore, 24500 joules of energy is produced by 24500. I'll just write it in a normal form, usual form. 38 and then 1, 2, 3, 4, 5, 6 kg. Okay. Then let's cancel this. My goodness, it'll be very small over the number. So 1, 2, 1, 2. And then we can cancel this by 5. 5 4s are 20, 5 9s are 45, 5 7s are 35, 5 6 are 30. 1, 2, 3. It's not divisible. Okay, so let's divide this. 49 divided by 76. So 0 point. So here will be 0. 176. 6, 6, 3, 42. 3. Did you get this? I don't think most of you got it. None of you? Okay, fine, no problem. It is difficult. Okay, from where? Okay, this first part, I think everyone got it. The second part. The second part, did you understand the efficiency part? No? Okay, fine. Let me explain the efficiency part also. Okay, see, what does efficiency mean? Okay, let's understand this. You'll understand this better when we discuss machine, but try to understand what does efficiency mean. Everything that we use in our life, right, has certain amount of efficiency. Okay, we, like for example, let's say that when you eat food, right, whatever food that you eat, do you think you convert everything to energy? No, a lot of it is wasted. Yes or no? So how much is wasted, how much is used, that is efficiency. Like for example, in this case, they're saying that fat has an efficiency of 20%. That means what? That means whatever energy that you give, you'll get back only 20% of it. Okay? Where does the rest 80% go? What is her goal? Her goal is to lift this dumbbell or whatever it is, right? Yes or no? So that is the work that she wants, right? She wants the fat's energy to be converted to this dumbbell energy. But does all the energy get converted to potential energy? No. Whenever you work out, you will see that you start sweating, you become hot, right? So a lot of energy goes in the form of heat. So the question is saying that only 20% gets converted to the potential energy. So what does that mean? The input energy is the fat energy. Okay, whatever energy that you're giving, that is the work input, the energy coming from the fat. Whatever you're getting, that is your potential energy. Okay, and this is nothing but the work output. And how do you define efficiency? Work output by work input. So efficiency is defined as work output by work input. You got this? Which part? This part you understood. What is efficiency? This one.
So, like, that one. You already draw the box.
This box. This box.
Like, what is the box?
Oh, the box is just like in
Explain the box.
with the box. You don't understand with the box. Like what did I explain with the box?
The one down with the box.
This part, no? Okay. Okay, let me explain again. See, this box is basically Natasha. Okay. In this case, the box is Natasha. What is Natasha trying to do? Natasha is trying to convert the fat energy to potential energy to lift the dumbbell. Yes? Okay. So now she's using fat energy. According to the question, the fat energy has an efficiency of 20%. That means what? Whatever energy that the fat gives, only 20% of it will be converted to potential energy. Rest 80% will be wasted, let's say, in the form of heat. That's what this part says. Did you get it? You sure? Okay. So the formula of efficiency will be work output upon work input. Fine. Till here you got. Good, you got. Okay. So if you use the formula of efficiency, work output. Now work output means what? What energy are you getting? So you're getting energy in the form of what? Potential energy. Yes. So the potential energy was how much? 4900 joules. Did you get it? Okay. Then work input. Work input is what? The fat energy, the energy that you are getting from the fat. So that we don't know how much energy we're getting from the fat, we don't know. So we wrote it just as work input. And then we did basic calculation and we found out that the amount of energy that the fat must give to Natasha is 24500 joules. Only when the fat gives 24500 joules, Natasha will be able to use that energy and convert it to potential energy of 4900 joules. Did you understand this part? Did you understand what are we calculating here? Huh? No? No? Did you get it or not? Okay, sure. Okay, fine. Till here is okay? Fine. Now we come back to this. Now this is known as elementary method. Okay, now what is elementary method? We know that this amount of energy is produced by how much fat? 1 kg of fat. That is given. We know that this much amount is produced by 1 kg. We want to find out how much fat is burnt to produce this amount of energy. So how do we do? It's like if I say 10 apples cost 50 rupees. What is the cost of 2 apple? Take your time. I understand you're tired. I'm also going slow. I'll repeat, yes. 10 apples cost 50 rupees. What is the cost of 2 apples? 10. How did you get 10?
For you to do like
Yeah,
you understand.
I understand. I have to. So first, he's basically trying to say that first you find the cost of 1 apple. Yes or no? So what will be the cost of 1 apple?
50 by 10.
50 by 10, which is 5. Then we find the cost of 2 apples. So that's what we did here. This much joules is produced by 1 kg. So first I have to find 1 kg is produced by how much? So 1 kg of joule is produced by this much amount of fat. If 1 kg is this much, then this will be this divided by this. If you don't understand, you can just memorize this formula that mass of fats is equal to work input divided by potential energy. Okay, I can understand that you're having problem with the elementary method, but trust me, it's not that simple. It's not that difficult. Okay, it's just you guys are tired. Huh? Why are you looking at you? My wish. Let's look at some important questions. Okay, these questions are important from exams perspective as well. Okay, so let's look at the first question. A ball of mass 0.2 kg is thrown vertically upwards with an initial velocity of 20 meters per second. Calculate the maximum potential energy it gains. You understand the situation? Okay, so a ball of mass 0.2 kg is thrown vertically up. Okay, so as it goes up, where will the potential energy be maximum? Here, 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 where? At its greatest height. So here the potential energy will be maximum, right?
Yes, sir.
So we have to calculate what will be the potential energy at this point. Now what is the formula of potential energy? mgh. We have m. Do we have h? Ananya. Ananya.
Yes, from
Stop.
height to receive.
Huh?
Height is from there to here.
Yeah, but we don't have the height. Yes or no? So how do we find the potential energy then?
So we can take M and G.
But we don't have h.
Oh, sorry.
Yes, Adasa? Huh? Force into velocity. But we don't have force. Something. You're close. We can do it that way also, the way you're saying. Okay. But I need you to understand something else. That's why I'm going to do it with a different method. See, when you are throwing it up, okay, what kind of energy are you giving the body? Kinetic energy. And that kinetic energy is being converted to potential energy. At its peak, all the kinetic energy has been converted to potential. That means this is what we can do. We can find with what kinetic energy did we throw it up, right? Once we know with what kinetic energy did we throw it up, that same kinetic energy was converted to potential. Did you get it? So that's what we can do. All right. So please write down given. So we got the kinetic energy to be 40. Since the kinetic energy is converted to potential energy, therefore potential energy must also be 40 joules. Question number 4 is similar to this. All right. A person swings on a rope from a cliff that is 20 meters high. How fast is the person moving at the lowest point of the swing? What does that mean? There's a person, okay, and he's swinging from what? From a height of 20 meters. All right. So if he swings, obviously his velocity will increase. You have to find out what is his velocity at this point. At this point. So how will you find his velocity at this point? Do you get the question? Huh? Hanging like this from a cliff 20 meters high, and then he is swinging, right? So as he goes down, his velocity will increase. What will be his velocity at this point, at the lowest point? How should we do? Velocity is equal to root 2 gh. Okay. So direct formula. Okay, we can do that. So we can use the formula. But I don't want to use the formula. Okay, you can use. I want to explain with the basics. Because since it's the beginning of the sums, maybe I'll just put it as an or alternative way. Please copy this. Given height is 20 meters. So that means what will be his potential energy? If he's at a height of 20 meter, what will be his potential energy? How do we calculate? Yes, people. Potential energy, what is the formula?
MGH.
mgh. So mass we don't know. G is 10, H is 20. So it'll be 10 into 20, 200 m joules. Right? Now see, this potential energy is being converted to kinetic energy. So therefore, we can write since the potential energy is converted to kinetic energy will also be 200 m. All right. Now we know the formula of kinetic energy. Half mv square is equal to 200 m. Then we can cut m and m both sides. This will go here. V square will be 400. Then v will be 20 meters per second. Let me know if you didn't understand. Or we can also do what Hadassah said, that is velocity is equal to root 2 gh. So it'll be 2 g is 10, h is 20. So square root of 400, which is again 20 meters per second. This is easier, but you have to understand this, that this formula can be used only when potential energy is converted to kinetic. Okay. And also this formula can be used only when the efficiency is 100%. Okay. We'll talk about it when we do some more sums. Okay. Let's look at this question. Question number 5. Okay. It's an interesting question. Okay. The diagram below shows a ski jump, right? A skier weighing 60 kgf stands at point A. So he's standing here at the top of the ski jump. He moves from A and takes off at B. So goes away. Got the story? Okay. A is at a height of 75 meter. B is at a height of 15 meter. All right. So, Grace, what is given? Mass. How much is the mass? 60 kg. Okay. Weight is 60 kgf, but mass will be 60 kg. All right. Okay, then Then we can take these heights also as HA and HB. So height at point A is 75 meter and height at point B is 15 meter. Calculate the change in gravitational potential energy of the sphere between A and B. So change in potential energy. Now what is the formula of change in potential energy? Anyone remembers? Or how would we find the change logically? Like his potential energy here was different from the potential energy here, right? So how do you find change?
GH2 minus MGH1.
Yeah, MGHA minus MGHB, right? I'm scared to ask also what. So change in potential energy will be mg, then we can take that common and we get HA minus HB. Then m is given to be
60 kg.
Yeah, thank you. G? Did they mention G? Yeah, G is 10. You're lucky if they mention it to be 10. It's the calculation.
Boards did not mention what we'll do.
9.8. Good question. HA is 75 minus 15. So 60 into, from here we'll get 66 is 36. 0, 0, and 0. So 36,000 joules is the change in gravitational potential energy. Okay. Question number B. Now B, what does it say? If 75% of the energy in part A becomes kinetic energy, calculate the speed with which the sphere arrives at B. Alright. So what is the question saying? Something like this. Whatever is the change in the potential energy, out of that 75% of the energy has been converted to kinetic energy. Right? Where did the 25% go? Krisha? Yes. Friction, yes. It got wasted, right? In the form of due to friction and air resistance. So it got lost in the form of sound and heat. Right? You got. So only 75% was converted to kinetic energy. Okay. Calculate the speed with which the sphere arrives at B. So what will be the kinetic energy? Kinetic energy will be 75% of the change in potential, right? So 75 by 100 into change in potential energy is 36000 joules. Then 1, 2, 1, 2. Multiply this. So this is the kinetic energy with which is going, but we need to calculate the speed. Now we can put the formula of kinetic energy. We know that kinetic energy is half m v squared. So that's going to be 2700. Please find v from this equation. Was the same. Okay, let's try one last question. You do this. Question number 6 on your own. See, what is the question saying? A hydroelectric power station takes its water from a lake whose water level is at a height of 50 meter above the turbine, right? So it's something like this. Imagine here's the lake, okay, and somewhere here is the turbine. Okay, here's the turbine. And what's happening is water, it falls from the lake onto the turbine, okay, onto the propellers of the turbine, causing the turbine to rotate, right? As the turbine rotates, it generates electricity. We'll learn about this in magnetism chapter, but for now just understand that the water causes the turbine to rotate. The rotation of the turbine produces electricity. Okay, let me explain in simple words. Okay, this electricity that you got is the power input or power output with respect to the turbine, of course.
Output.
The power output, right? So this is the power output. This is what you got from the turbine. So where is the power input? Whose giving the power input? The water, right? So the water is giving the power input. Now the water has energy stored in terms of what? What kind of energy does the water have right now? Potential energy. So that means this power input, isn't it due to the potential energy of the water? Yes. So basically, the potential energy of the water is being converted to electricity. Okay. This question is special because here they're saying per second. Since it is saying per second, so it does not matter whether we use power or energy, they'll both be same. Given height is equal to 50 meter above the turbine, assuming the efficiency is 40%. Calculate the mass of the water flowing through the turbine to produce a power of, so power output is 1 megawatt or 10 to the power 6 watt. Okay, this is given is fine. Okay, let's use the formula of efficiency. Now efficiency is power output by power input. Since efficiency is given in terms of percentage, we can write 100% or we can write this as 40 percentage is equal to percentage, we can write divided by 100. Power output, which is the power output, directly we can write 10 to the power 6 divided by power input. This is what I was saying. Irene, you have written work here. It should be power. Okay. Now if you cross multiply, power input will be, let me write this in the expanded form. 1, 2, 3, 4, 5, 6 into 100 divided by 40. And we can cancel this, 2, cancel this, 5, 1, 2, 3, 4, 5. Then we can cancel this again, 2, 5, 1, 2, 3, 4. So we get 25, 1, 2, 3, 4. 25 lakh watt of power is required. So 2.5 megawatt will give you 1 megawatt. Okay, let's break this down. Till here, did you understand? Does anyone have any doubt till here? Yes, anyone? Nafi? This part you got? Yeah, this is the definition of megawatt. 1 megawatt is 10 to the power 6 watt. Like we have kilo, kilo is 10 to the power 3, mega is 10 to the power 6. Okay? Okay, fine. Then you got this till here. You got till here. Okay. Okay. So that means this power input is given by the water, right? This much energy, this much power is given by the water so that we can get this much amount of power, right? Now, what is the formula of power? Work input divided by time. So that must be 250,000 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 watt. Now, work done by whom? By the water, that is the potential energy. So work done will be mgh, time is 1, is equal to 2512345 watt. Okay. Okay. Again, this line is also difficult. This you got it? How? Why work input is mgh? Did you get it? Again, I'm repeating. Why work input is mgh? Because here the input work is done by the potential energy of the water. And potential energy of the water is nothing but mgh. Yes. So that's why it will be mgh. Got? Okay. Then after that is very easy. M, G is 10, H is 50 is equal to 2, 5, 1, 2, 3, 4, 5. So 0, 0 we can cut. 5, 5 is 25. Then we get M is equal to, right, 5,000 kg. So see the amount of water that is so large. 5,000 kg of water is required just to produce 1 megawatt of energy. You comment on my YouTube comments. Report?
Only 20 subscribers. You can move a new channel.
19.
No, sir, 20. I checked this morning. Check, sir.
20 or what? Who subscribed?
Sir, I subscribed all about.
You haven't.
I have
You haven't subscribed.
I had a question, so why?
Yes.
We should be.
Because you guys look at your condition, you guys are not understanding simple stuffs.
Stuff.
What stuff?
Stuff is already numerical.